This computer. Okay, before we start the lecture material, is there any questions on course logistics or material from last time? Okay, nothing online. So if I forget, remind me to, I'm going to say a few words about project 2 at the end of class today. So if there's nothing else, we're going to dive right in. Okay, all right. Whoops, decline. Okay. All right. So okay, so today we're going to switch gears a little bit and start talking about sort of the mechanisms of relaxation, which is really one of the fundamental aspects you'll see in clinical MRI. We'll introduce the concept of gradient and spin echoes, and then we'll dive into image contrast, and hopefully we'll have time to at least start functional MRI. But before we do that, I think everyone did pretty well on the pre-lecture quiz, so that's good. And I think the one thing that I just want to emphasize is that, so remember with grappa, basically each coil is sort of reconstructed on its own, okay? So you can have it such that, all the coils have good profiles, but one doesn't have good profile. So in that one question, we're specifically asking about coil 1, it's sort of like coil 2 was there were combinations where the combination of coil 1 and 2 was worse, but the one where coil 1 was the worst, which is where it had the flattest spatial profile. So therefore it's going to have the narrowest K-space profile. So that would be worse for grappa. Okay. So that was sort of, I think even though there were 2 attempts, there was still some uncertainty about which one was the worst one. So specifically for both Sensa and grappa, obviously one coil being bad can have an effect, but for grappa, it's just much more obvious because then you actually reconstruct each coil on its own. Okay. Any questions about that? Okay. If not, let's review relaxation. And so we've already had a taste of this in terms of, we've already defined what T1 and T2 are. And we've said that T1 governs the return to equilibrium of the longitudinal component, and T2 governs the return to equilibrium of the transverse component. Okay. So today we're going to take a deeper dive into what that actually means. And so, and this was just summarizing that the longitudinal component recovers exponentially back to its equilibrium. The transfer component processes and decays exponentially. And in fact, in your homework, you showed that T2 must be less than T1. Okay. Otherwise, the length of that vector is going to be greater than m sub naught, and that's not physically possible. All right. So today we're going to get into why do different tissues have different T1s and what governs T1, and also why does T1 change with field strength. Okay. So the idea behind this is here, we need to start thinking about how atoms and molecules interact with each other. Okay. And the idea is although we're not going to talk too much about quantum mechanics, we can think about, we've talked about energy levels, right? And we've talked about how something that's aligned with the field has the lowest energy level, and it takes energy to send it into a different energy level. So if you go back to very simple, underlying all this is this concept of spin up and spin down, okay? And the spin up is going to have the lowest energy level, and the spin down has the highest energy level. So the idea is, if you're in a low energy state, a high energy state, how do you, what determines how you give up energy to your surroundings to go back to the low energy state? It turns out that energy difference in MR is quite small. So the probability of that happening on its own is very small. So the probability of happening on its own is called simulated emission. This is something Einstein looked into a long time ago and sort of discovered the basic mechanisms behind that. So it's fairly well understood, the equation. And it turns out if you just accounted for things just to naturally just jump back to their lowest energy state, things would take a long time. Okay. So it turns out that what you need is, like, if I'm sort of a spin that's at a high energy state, it's very unlikely I'm going to jump to a low energy state just on my own. Okay. So what it means is I need to have something, I want to give up my energy to the environment. Okay. So I need to interact with some other molecule that can absorb my energy, okay? And the molecules that can absorb my energy the best are the ones that are going to be at the same resonant frequency, okay? So the idea is, like, if I was just sort of moving my hand like this, and I wanted to sort of transfer my energy to somebody else, it's going to be easiest if they're also moving at the same rate, okay? If I run against someone who's not moving, it's going to be hard to do that, okay, to transmit that energy. So the idea is that the rate at which this spin can give up its energy to the environment is best if it can interact with molecules that are going at the same rate. And so then that'll turn into sort of like essentially vibrations. Okay, so mechanical, we're going from this, we're going to turn it into mechanical vibrations. Okay, so so that's why you have this, what we see here in this curve here. And these are really, if you want to delve into deeper, the MRIQuestions.com actually has a fairly good introduction to all this. So that's a great source for those of you who want to learn more. But this is the main curve that you want to keep in your mind, that the T1 relaxation rate has this U-shaped curve with response to the molecular tumbling rate, okay? And so the molecular tumbling rate is sort of, you can imagine these molecules just due to thermal action, they can sort of tumble, and rotate. And if I have a proton that's rotating, it's actually got sort of creating its own magnetic field that's rotating, right? And so if it's rotating at the right frequency, then this can give up its electromagnetic energy to this proton, okay, or to this molecule. So it turns out that there is sort of a special frequency. So when the Larmor frequency is equal to the molecular tumbling rate, that's the sweet spot. That's where the relaxation rate is the smallest, okay? So that means the relaxation rate is the fastest, or the T1 relaxation time is the smallest, all right? So low T1 is where you're matching the environment. If the environment is tumbling too fast, your T1 goes up. So that's why T1 of water is very long, or T1 of any fluid in your body is very long, because the water molecules can tumble very, very fast, okay? Similarly, if you go into bone, those molecules don't tumble very fast either, right? And so you tend to have longer T1s in anything that does not have a high tumbling rate. So it's really, the T1 tells you a little bit about the sort of the mechanical tumbling rate of the environment. Okay, so that's sort of what this website calls the Goldilocks principle. So I think some of you have heard of it, Goldilocks and the Three Bears. Others of you have not. So you can just Google Goldilocks and the Three Bears. Essentially, she eats porridge, and this is, I guess, too cold, too hot, just right. So when the tumbling rate is just right, that's when the T1 hits its sweet spot. Okay. So that's T1 in a nutshell. And so let's see what happens, why basically T1 increases with field strength. So one observation is that as you go to as people build these higher and higher magnets, T1 becomes longer. That has some advantages, but it also has disadvantages. As we'll see later, T1 is sort of how fast the magnetization grows back, okay? So the longer it takes to grow back, that means you have less magnetization to use for the next excitation, all right? And we'll see how that affects our MRI pulse sequence design. But let's just look at this thing here. So this is looking at molecular tumbling rate and showing that, obviously free water can have a range of tumbling rates. Macromolecules like fat tend to have low tumbling rates. And then bound in sort of normal water and tissue has these tumbling rates. And so when you're at this field strength and the Larmor frequency is in this region, there's a lot of molecules it can interact with and give up its energy, okay? But as I go out to here, and my frequency is much higher than most tumbling rates, then there's much less for it to interact with, and it's really only acting with free water and maybe some of the tissue. So that's why we find in biological tissues that the T1 tends to go up with field strength. So fats and oils sort of tend to have, as we said, lower tumbling rates, and so they'll have longer T1s, and so that you sort of get very bright fat in some of your images. Okay, so that's T1 in a nutshell. Now we're going to switch to T2. Okay, so remember, T2 is basically, once we've tipped the magnetization in the transverse plane, the length of this magnetization vector shrinks down to 0, okay? So the main mechanism behind this is slightly different from T1. I mean, there's mechanisms that affect, T2 is affected by both mechanisms, but the main one we're going to talk about is qualitatively different. And it's related to the fact that we never think about one spin in isolation, right? When in MR, we're looking at voxels, maybe it's a millimeter by a millimeter. So there's many, many spins in there. So we really need to look at what's the overall net magnetization of spins in that voxel, all right? So the idea is, if I think at t equals 0, I excite all the spins and they're all aligned, okay? They're all in phase. And now what happens is, over time, they get out of phase. They can process at different frequencies, okay? So now, see, if they get out of phase, some go slower, some go faster, and over time, they get more and more out of phase. So the net sum of this, if I think about the net vector, I'm going from here to here to here, okay? So that net magnetization is decaying with T2. So if I look at relaxation time versus tumbling rate, instead of this U-shaped curve here, I get this very different shape, okay? Where at very fast tumbling rates, okay, T2 is very long. At very slow tumbling rates, it's very short, and somewhere in between, it's sort of in the middle. So that means that in liquid, such as water or say for cerebral spinal fluid, you're gonna have very, very long T2s, okay? Up to like 2 seconds, 3 seconds. It'll just last a long time. The signal will last a long time. If I'm in like bone or tendon or ligament where things are very bound, then I'm going to have very short T2s on the order of less than a millisecond. So the signal just disappears almost immediately. And then somewhere in between, like in brain, it's typically on the order of 100 milliseconds. Okay. So the question is, why does that have, what's going on here? Why does this have a very different shape? So what you want to think about is, in any given sample, you imagine I have lots of different spins, okay? And each spin, remember, is its own little magnet, okay? So imagine I don't have another, oh, here's a pencil, okay. So let's say I have 2 spins, right? And this is rotating around its own, and so it's got a magnetic moment. Now imagine this spin is moving around very quickly, okay? So every time it moves, so if it's moving out really fast, every time it moves, it's pointing in a different direction. So the time average of its magnetic field sums to 0. So this spin's like, from this spin's point of view, this spin is like has no effect, right? Because its effects average out, okay? Because it's pointing here, 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 here. So on average, it's 0, okay? If it's moving very slowly like this and not tumbling very fast, then it's got a magnetic field that can affect the precession of this magnetic field, okay? So then the interaction of all these spins on each other gets them, so this sort of maybe makes this go a little faster, but a spin here would have a slightly different effect on this spin. So these 2 spins would get out of phase, okay? So the idea is the quicker things can move, it's what's called motional averaging. Okay, so then the B, sort of the B of the neighbors goes to 0. Okay, so neighboring spins don't really affect each other. All right. It's a sort of, you can sort of think about it like you're in a crowded room, right? And people are speaking really, really fast. All the sounds will sort of overlap with each other and you won't really hear anything, right? You won't be able to pick up any signal. But if people are talking very slowly, and you might be able to sort of pick up conversations and things like that. So this is what gives you sort of this characteristic dependence of relaxation time on T2. All right. So let's look at some typical T1s and T2s. So as we talked about before, anything where there's a high tumbling rate, say water and CSF, which is CSF is cerebral spinal fluid, then let me just make sure this is recording. Yeah, it is. Okay. You can sort of, the T1 here is pretty long, 4 seconds and 2 seconds. Okay, so that means the signal lasts if I tip the magnetization, I have quite a long time while it's processing around. But in most tissue, like gray matter, muscle, liver, fat, I only have on the order of 50, 100 milliseconds. So that means I got to get that signal very quickly. If I go into tendon, I'm down to 5 milliseconds. If I go into proteins, I'm down to 0.1 or 1 second. And if I'm in ice, I'm down to 0.001 second, right? Because the molecules in ice don't move very quickly. Okay. So you sort of see this T2 is going down pretty quickly, right? Whereas if you look at this, the T1 has this sort of, it's going down and it comes back up for ice, okay? Because you're seeing that essentially as it can sort of resonate more. And so here, obviously, the fat for this frequency, the fat is at the sweet spot, right? The T1 is the shortest at 1.5 Tesla. And then ice takes a long time, okay? So that's the basic idea. Okay, so with that, this is the question you have. So Dr. Block has a vial of liquid with T1 of 1,000 and T2 of 1,000. He adds some gelatin to the vial, mixes the solution, allows it to gel. What would be reasonable values for the T1 and T2 of the new mixture? Okay, so I'll launch the poll online so you guys can participate as well. Let's see, how do I do that? Launch. Okay, so maybe take about a minute to think about this, and we'll regroup in about a minute. Okay, let's sort of see what people think in class. So at the count of 3, just sort of say loudly what you think the right answer is. 1, 2, 3. D is, I think, what I heard. Okay, so let's see what we think about. So first of all, which of these cannot be correct, right? We know that T2 can't be greater than T1, right? So we can certainly rule out this one here. And I think that's about the only one we can rule out, right? Or C we can rule out, right? Okay, good. Okay, cool. So even if you didn't have any information, you could rule those out right away. Okay. So now, obviously, if we add gel, there's going to be less rotation, right? So the tumbling rate's going down. So we know T2 has to go down, right? So obviously A and B can't be correct. Okay. So now we're left with either D or E. Okay. And so let's think about that. So we know that T1 has this dependence here, right? Okay, and we were at 1,000, right? So we were at 1,000. But the problem is we don't know where we are on this curve, right? We could have been here, in which case T1 would go down. Okay, or we could be here, in which case T1 would go up. Okay, so actually both D and E, given the information you have, are possible. Okay. Okay, any questions on T1 and T2? All All right. So now I'm going to talk about what's called static and homogeneity, so work our way up to the spin echo. So the idea is when we buy these, when we pay millions of dollars for these magnets, the magnet is specified to be very uniform over a certain volume, typically like a 30 centimeter, typically a 50 centimeter sphere. So it's good enough for most bodies. And so there's a lot of time spent, and that process is called shimming, where they actually put in little metal sort of iron pieces at different places. And then they also have additional coils to make the field very, very uniform. Okay. So that's where you want to start off with. You want to start off with something that the instrument itself is ideal. Okay, as close to ideal as possible. But then what happens is you put in like a body or a head or whatever, and all of a sudden that uniform field becomes non-uniform. Okay, because the biological sample interacts with the magnetic field. Okay, so we want to talk a little bit about what that does to our imaging and our signal. So the idea is this, that, from sort of your previous physics courses, you probably have some sense that you've heard about like diamagnetic or paramagnetic or ferromagnetic, right? For this course, you can just sort of assume that if I'm in a uniform field and I put any object in it, it's going to either have a negative or positive, what's called susceptibility. Okay. So here, if it's diamagnetic, you can imagine, first order, you can imagine it's sort of repelling the magnetic field. It's acting against the magnetic field, right? The field will tend to go around it. And if it's para or ferromagnetic, such as iron, it will tend to concentrate. It's sort of like it adds to the field, and the field will get stronger inside. Okay. In any case, we've gone from this uniform field to something that's quite non-uniform. All right. I'm not sure we'll talk about it in this course, but there are people take advantage of this to create molecular contrast agents. So gadolinium is a very popular contrast agent, okay, which because it affects the magnetic field around it, it is used a lot in the clinic. Okay. Okay, so what I'm showing you here is 3 images. It's the same head. We're just going up slice-wise. We're starting here and just working our way up through the head. Okay. And so these are sort of what the anatomy looks like. And these are images of the field. So the darker might mean the field is lower here, it's higher here. Okay. So this is the front of the head. So why do you think we're getting this field homogeneity at the front of the head? Any ideas? Is this normal, abnormal? If you saw this, would you be worried about your patient? Does this person need surgery? Okay. So what's going on? What does anybody sort of okay, let's see, there's something online. But it is original liquid can starting point of T2 evenly lower than turning point. Yeah, thank you for your question online. I'm not really sure I understand the question, so feel free to sort of rephrase it or ask in office hours. But essentially, for that question, we're going from a high tumbling rate to a lower tumbling rate. Okay. Okay, so getting back to this question here, is there any sort of major difference in the tissue? Like at the front of the head, what's different about the front of your head versus the back of your head? Obviously, you have eyes and nose. And what else do you have? Okay. So does anyone know what a sinus is? Has anyone had a sinus infection? Hopefully not. Maybe you have. Okay. So you have these big air pockets here, okay, which are good because they make your head a little lighter. Otherwise, if you had bones here, it'd be much heavier. Your face would be much heavier. But those are essentially, you have these big sort of, otherwise you would have a uniform. So you think of your head as like a uniform thing, but you got these big air pockets in it. So those big air pockets are where there's going to be a big difference, like air and tissue have different susceptibility. So around those areas, you're going to have a lot of change. And those are quite, the shapes of those are such that they're not slowly varying, right? They're like these weird, they're quickly varying in a pretty small amount of space, right? So you're gonna have these weird field homogeneities around your sinuses, okay? So what happens in those areas? Why are we getting, so if you have a lot of field homogeneities, we wanna think about what that does to the MRI signal. So imagine you're in an area at time equals 0, you tip all the spins into all in phase, and so you have this magnetization. And assume they're in the presence of a sphere which has this magnetic field pattern, okay? So here's a stronger field, here's a weaker field. So we know from previously, we know that if I'm in a stronger field, I'll process more this way. If I'm in a weaker field, I'll process more that way, okay? So there is going to be, if there's some inhomogeneity, there's going to be some dephasing, okay? And therefore, my signal, if I wait some amount of time, it's going to get smaller. Now, if I make the field inhomogeneity even stronger, I'm going to have even more dephasing, and the signal is going to decrease even faster, okay? So it turns out the MR signal, and we're going to see how we use this in functional MRI, is very sensitive to how much inhomogeneity there is. Okay, and this is one of the ways we use the MR signal to see what's going on in biological systems. Sorry, this is a very busy slide, so let's just focus on what matters. Essentially, previously we had this T2 decay. Now we're going to add this additional T2 prime component to account for the static dephasing, okay? So the T2, remember, is due to random tumbling, okay? So that's just, since it's random, there's not much we can do about it, right? It's just it's sort of the inherent property of the tissue. All you can do is change the tumbling rate by either cooling or heating the object or adding gel to it. But typically in a clinical environment, you're not going to do that, right? You're not going to freeze your subject. You're not going to heat them up. You're not going to like inject agents into their body, aside from contrast agents, which you can do, okay? But turns out static dephasing, actually, it turns out there is something we can do about it. But let's look at its effects. So we're going to introduce this new time constant called T2 star, okay? And T2 star is essentially 1 over T2 star is equal to 1 over T2 plus 1 over T2 prime. Or the other way we write it in the field is R2 star equals R2 plus R2 prime, okay? Where this is just 1 over T2, and this is 1 over T2 prime. Right. And so for those of you sort of who are more, chemistry oriented, this makes a lot of sense, right? I mean, this is one rate of reaction and another rate of reaction, and overall the rate of reaction is the sum of those two rates, okay? So as I said before, keep in mind, the T2 is due to random motion of spins. So it's random, so it's really not reversible. You can't really run time backwards, okay? But this is due to static homogeneity. So it turns out it is reversible. And it turns out under certain circumstances, if you want to, you can get rid of it, okay? So now we're going to introduce the term gradient echo, okay? So today we're going to talk about two things that you'll hear in MR all the time, gradient echo or spin echo, okay? And you can think of an echo as typically anywhere where we revisit kx equals 0, okay? Where we're that's sort of where we're going to define echoes. So for example, if we look at this, for now, we're going to ignore what this looks like. We'll talk about what this is doing, but we have an RF pulse that excites the magnetization. And here you're seeing the spin warp gradients we talked about before, where this is the readout gradient and these are the phasing code gradients, okay? So remember the readout gradient, once these two areas cancel out, we're at the center of K space, Kx equals 0, okay? At that point, for example, if our object was a direct function, at that point, ideally, we would have a sinc function, and that would be where we'd measure the sinc function, okay? But if I have a T2 star, what's happening is, as I measure that sinc function, it's being weighted by this exponential decay. So in fact, what I would measure is, this is the sinc function weighted by this exponential decay, okay? And so that's the fact that this refocusing or kx equals 0 is due to the gradients just balancing out is why it's called a gradient echo. All right. So let's look at system susceptibility artifacts. Let's look at this one first. So this is a subject who came into the MR scan and obviously does not have a mouth. Okay. So what do you think we should do here? Is this person like, does this person have a huge deformity? Do we need to send them to oral surgery? Or is this just an artifact? Obviously it's an artifact, but why is this artifact here? What do you think is going on with this person? Why are they missing their mouth? Something in their teeth, right? Maybe braces, right? This is probably a young person who has lots of braces or lots of dental work. So this is one of the counterindications, or, when we scan people for research studies, we always need to know how much dental work they have, because if you have a lot of dental work, guess what? That's going to perturb the magnetic field, okay, and cause a lot of dephasing and make it disappear. Okay. Now, if you're not imaging the mouth, maybe you can still get away with it because you sort of notice that this part is okay. But in some cases, especially if you're trying to do very sensitive measurements, it may not be okay, because if they're moving slightly, that can change how that magnetic field interacts with even farther regions. Okay. In fact, it turns out even when you breathe, the fact that your lung changes volume changes the magnetic field around it, and that actually can affect the signal all over. Okay. Okay, so the question is, wouldn't metal and braces be ripped out at extreme velocity from an MRI? Okay, luckily, generally not, because they don't have that much mass and the force is, and they're pretty tightly in there. But it's generally not a good idea to go into an MRI machine with braces, simply because if something is a bit loose, it will become looser. Okay, yes.
Well, I'm thinking, is it possible to induct them?
Yes, that's also possible. And that's another reason not to go in, because it can actually induce current. And that's why we need to make sure. So even actually now, it's a great question, because just this year we've had to change our screening policies, because now more and more, I don't have any, but there's like the newest trend in fashion is to have like smart clothing, right? Where you've got wires and stuff in your clothing. Does anyone know more about this? I don't know enough about this, sorry. But yeah, so now we have to screen for special clothing. Like we have to make sure the clothing isn't like, electrically active now, okay? And then a few years ago, a lot of people were getting tattoos, and tattoos have metal in them. And so, especially if you have tattoos on your face, it can be very sensitive and cause current, issues in that. So yeah, yeah, so there's a lot of interesting things that happen. So basically, yeah, the RF fields, it can introduce artifacts, which probably are not an issue. The other issue is when we put the RF fields in, the MRI machine is essentially like a microwave, right? So if you have metal, you know what happens if you put metal into a microwave, right? It'll explode or cause heating, right? And so the same thing is that if you have metal in your body, or wires anywhere, that's the other issue that we worry about, is heating. Okay, and then burns due to heating. So that's the other problem that happens. Okay. So bottom line is, if you're getting an MRI scan, just wear your sweat clothes. Don't wear anything like that has metal in it. Okay. This person here, what does he think's going on with this person? Does this person have holes in their bone? Yeah, they had surgery. Okay. So so this is actually an active field of research, is how do you scan people with metal implants, right? If it's titanium, it's at least it's not, going to be pulled out most likely, but it can still, depending on the imaging you're doing, can still have some magnetic properties to it. And so how do you scan people with metal implants is something that the manufacturers work on. Okay. Because obviously, if you are in a hospital being scanned, you probably have other, it's likely you're going to have, probably had surgery before or something. Okay. The other cool thing is, as I said before, one of the really cool things about MR is that one person's artifact is another person's signal. Okay, and we're going to see that. So in one case, susceptibility is like, we don't want it, right? You want to get rid of it. But actually, in some cases, you're like, hey, I actually want to see the susceptibility. So this is one example here where they're using what's called susceptibility weighted imaging to make really beautiful pictures of the veins. Okay. So what do you think is causing the susceptibility in this picture? Any ideas? What do you have a lot of in your veins that's magnetic? Go ahead. Hemoglobin, yeah. And specifically deoxyhemoglobin. Okay. And so this is basically measuring the susceptibility due to deoxyhemoglobin. Okay. Which is what we'll talk about when we talk about functional MRI as well. Okay. So let's say that you actually want to get rid of those artifacts, though. That's where the spin echo comes in. And this is one of the key concepts. So typically when you get an MR exam, one category is it's either going to be a gradient echo scan or a spin echo scan. Okay. And so let's talk about spin echo. Remember, T2 and spin echo is to deal with the T2 star decay, okay, or the T2 prime decay. So imagine that all the spins are aligned and then they dephase. But in this case, the dephasing is not due to random motion. It's due to the fact that they're in different parts of the object. Okay, they're experiencing different static fields. Okay, so you notice this person, imagine these are runners in a race. This spin gets ahead and this spin lags behind. Okay, so let's say you allow them to go for 1 millisecond until they get out of phase. Then what you do is you apply 180-degree RF pulse, okay? And this is what's called the pancake flip. So this spin here, this spin here got ahead, and this spin here lagged behind, and this spin here is right in the middle, okay? So you take this spin that's really fast, and you flip it back to the back of the line, and the spin that was at the back of the line, you flip it to the front of the line. And you wait another millisecond, guess what? The one who's fast is going to catch up, and the one who's slow is going to fall behind, and then everything's going to align. So that's the trick behind the spin echo. Okay, so it's the same thing if we all ran a race, right, a 1 kilometer race, and at half a kilometer, I made the front person go to the back and the back person go to the front, and we all kept at the same rate, then at the end, we'd all end up at the same time. Okay, so essentially, it's sort of like a form of handicapping, right? You sort of make the fastest person lag behind, and the fastest person, you give them a head start. Okay, so it turns out that, oh, and the other term I'm going to introduce here is echo time. TE is echo time, okay? Or time of echo, but typically we'll call it echo time. So echo time is where everything refocuses and we get this echo. And the idea is we wait half the echo time, apply the 180-degree pulse, and then the remaining half of the echo time, the spins are refocusing. Okay. So this is a movie from Brian Hargraves at Stanford that shows that. So they just get out of phase, then you flip them, and they get back in phase. Okay. So this was invented by Erwin Hahn in 1950, and it's been a very important part of MRI and NMR ever since. Okay. So now what we're going to do is introduce what we call the spin echo pulse sequence. So it looks exactly like what we had before, except now we have this 180-degree pulse. Okay. And this is that pancake flipping pulse that we talked about. And so at echo time, T equals echo time, okay, I have this sync pulse is now weighted by e to the minus t over t2, okay? Whereas for gradient echo, this was t2 star, okay? So basically, this has gotten rid of the t2 prime weighting just at the refocusing time. But notice, there's only going to be one time where they're totally refocused, right? If I'm a little away from it, I still have an effective t2 prime that falls off as I get away from that echo time. So I can't totally refocus it all over the entire case space, but at least I'm refocusing it at the center of case space. And remember, the center of case space is sort of your average signal. So that's why we typically use the center of case space as sort of where we define echo time. All right. Okay, so what does that do? Well, in this example here, they purposely created some uniformities in the field. And if they used gradient echo, you would see all these dark bands here. And these dark bands are areas where there's a lot of non-uniformity in the field. Okay. And if I do spin echo on exactly the same phantom, magically that goes away. Okay. So this is really important for areas where you feel like there's a lot of inhomogeneities. You really want to see the underlying structure. So there you would use a spin echo. Okay. And there's variations of that now called like fast spin echo. I don't think anyone's doing a project on fast spin echo this year, but yes.
So I understand why you'd want to do spin echo
Yeah.
over gradient echo, but why would you pick gradient echo over spin echo?
Yeah. So that's a great question. There's a couple of reasons. One is you might want to emphasize, like what we'll see in functional MRI, we use gradient echo because we really want to emphasize the T2 star dependence. That's a signal of interest, right? Another case is where you want to go super fast, okay? So the problem is introducing these 180s introduces more time, and also the 180s have what's called, they're RF pulses, so they have more RF energy. And so if you want to go really fast, you can't just keep hitting your sample with that much energy. And so there are cases, for example, when you first go into a scan session, the first thing we do is typically we do some localizer scans, which is very fast scans to sort of see where the person is. And then we do our prescription based on that. So those are typically gradient echo scans where essentially you want to just go very fast, okay? And so, and then the idea is if I keep the echo time very short, okay, then there's not much time for things to dephase. So in any scan where I can keep the echo time very short, so there's not much time for things to dephase, then I can use a gradient echo. If I need a very long echo time, as we'll see for like for T2 weighted imaging, then I need to use a spin echo. So actually that's a great segue, because essentially we'll spend the rest of the lecture talking about is sort of picking these parameters and what determines these parameters, okay? But let's just review. Oh yeah, so before we do that, does that answer your question? Okay, great. So let's just review a little bit of what we talked about. So we have longitudinal relaxation, which is just M sub Z recovering, okay? And then we have both T2 decay, which is due to random motion. And then if I add T2 prime onto that, then we get T2 star decay, okay? So T2 star is always going to be less than T2, okay? Because you've got both the random effect plus the static dephasing effect, okay? So that's one thing to keep in mind. And that this static effect we can somewhat reduce by using a spin echo and get back to T2 decay, all right? Okay, so now we're going to talk about how do we actually take advantage of the fact that different tissues have different T1s, T2s, and T2 stars. We're going to talk about 3 different types of imaging: proton density weighted imaging, T1 weighted, and T2 weighted imaging. And the way we're going to do that, at least the most basic way we're going to talk about today, is we're going to adjust echo time and TR, or repetition time, okay? And so if you sit down to any MRI console in the world, you'll always see echo time and TE and TR are going to be 2 of the things that you need to specify, okay? So let's talk a little bit about what, we're going to stick to what's the simplest thing, which is called a saturation recovery sequence. Essentially, that means I use a 90-degree flip angle to tip the magnetization, and then it starts off at m's equals 0 and then just recovers. Okay, so it's saturation because I've started off at m's equals 0. And then I wait some amount of time and I acquire the center of K space at TE echo time. And then I wait for the M sub Z to regrow before I hit it with another 90-degree pulse. Okay. And so the gradient echo sequence is represented as this. I have the density of spins in any voxel. I have this T1 recovery, and I have this T2 star decay. So that becomes the equation that I'll use, okay? And it's T2 star because it's gradient echo, right? If I have a spin echo, it's exactly the same thing. I apply the 180-degree pulse halfway between my excitation pulse and my echo time. And now the equation is exactly the same, except now I have T2 decay. All right. So let's say I want to make something that doesn't really depend on T2 or T2 star. Okay. So that's what I'm calling a T1 weighted scan. Okay. Notice if we go to these equations, there's really nothing I can do about this term here, right? Proton density is what it is, right? It's just there. Okay. Now, especially with this one, there's nothing I can do about it. Now, but let's look at what we can do with the T1 term and the T2 term. So let's say I want to make my sequence insensitive to this term, right? So notice if I make TE go to 0, this term just becomes 1 in both cases, right? So the idea behind a T1 weighted sequence is I want to make TE very, very short so that I'm only sensitive to proton density and the value of T1. Okay. And so the principle, and now the idea behind T1 weighted contrast, this is a thing from the book, is that if I have a short T1, it recovers very quickly, okay? And I have a lot of magnetization at the next excitation. If I have a very long T1, the M sub Z recovers very slowly, so I have less signal at the next excitation. So based on the T1 of the tissue, the signal is either be brighter or less bright, depending on. So long T1s will be less bright at the next excitation, and short T1s will be brighter. Okay. So let's look at a T1 weighted scan. And in this case, I'm going to assume that I have two tissues, and I'm going to assume the proton densities are equal. Okay. So these are the saturation recovery of the two. So T1 of 800 milliseconds, you see recovers more quickly than a T1 of 1200 milliseconds. Okay. So typically in MRI, we're trying to, with all imaging, we're always trying to talk about contrast, right? What's the difference between two different tissues? Okay. So as a rule of thumb, which you'll use in your, I'll talk about it at the end of class, but for the last homework, we'll just have like one very short problem on it. Okay. And it's just applying these rules of thumb. So the rule of thumb here is if these two densities are the same and these have the curves, this is the difference between those two curves. And you can sort of see it reaches a maximum difference right around the average of these two values. Okay. So the rule of thumb is if you have two T1 species and you want to figure out the TR that maximizes the contrast, just take the average of the two. Okay. So the rule of thumb. It's just average. All right. Question. We'll get to that. That's a great question. Yeah. Okay. In fact, that's something you'll look at in your homework too. Okay, so let's look at some T1 weighted images. So for example, we talked about how fat has a fairly short T1. And so if you're looking at, so for example, this person unfortunately has some sort of fat, let's see, which one is this? Lipoma of the corpus callosum. Okay, so he's got a lot of fatty infiltration of the corpus callosum, which is essentially the major highway of fibers that connect your left and right hemispheres. Okay, so I'm not sure what symptoms this person is experiencing, but this is not what you want to see on a normal image. Okay, so for things where you're looking at fat, unfortunately, another issue that's happening a lot in today's society is fatty liver disease, right? And so a lot of fat in the liver, which is also not good for you. Okay, so that's T1 weighted scans. T2 weighted scans are, we want to get rid of the T1 dependence, right? So we want to make that 1 minus e to the minus TR over T1 term go away. Okay, we want to make this go away, right? So the way we do that is we make TR very long. Okay, so in that case, this term would just go to 0 or just go to 1, right? Okay. So now this is a T2 weighted scan. And so we have proton density with this T2 weighting. Okay. And we can play the same game. Here, once again, I'm assuming these tissues have the same proton density. And here, T2 of 80 milliseconds decays faster than T2 of 120 milliseconds. This is the difference, and you can sort of see the difference is once again maximized at approximately at the average. Okay, so once again, that's the other rule of thumb you can apply. And so here's an example of a normal T2 weighted scan. Okay. And here's an example of someone who has a lot of fluid. And so there's a cyst here. And so this is, remember, fluids have very long T2s. So that means if I have something that's sensitive, weighted to T2, it's going to be any fluid is going to be very bright. And so you're seeing the brightest aspects of this signal is the ventricles. That's where you have a lot of fluid. This person also has that in the ventricles, but you can sort of see this cyst is actually pressing in. And so this ventricle is sort of deformed here, right? There's a lot of pressure from that cyst pushing onto the tissue. And you can sort of see this is totally filled with fluid. Okay. Okay, and the last thing you can do is proton density, which is you just make TR very long, get rid of that, and make TE very short. Okay. And what does very long and very short mean? Well, typically very long, you make the TR as long as the system will allow you to make it. Okay, so typically in a problem, it'll say your maximum TR is this. Okay, so typically that's about 12 seconds or 15 seconds. And then the shortest TE is also determined by your system. And so typically you'll be told, well, the minimum TE you can do is like 5 milliseconds. Okay, so you just go to the limits. Okay, if you can. And if you do that, the result is proton density weighted. Okay. So this is a proton density weighted scan in a person with I forget what the PP stands for, but it's a type of multiple sclerosis. And what you're seeing here, it's sort of hard to see, but this is white matter here. These are sort of the white matter tracks, and that's supposed to be sort of low proton density, but you're seeing areas here where there's sort of more proton density than you would expect. Okay. So indicating something's going on with the white matter for those, multiple sclerosis essentially attacks the myelin around the fibers. And so they're seeing it here in this subject. There's more for those of you who want to follow up on that. There's the link here. Okay. Okay. So let's do this exercise together. If you do this exercise, essentially you just repeat what we do on the homework. It shouldn't take you more than 15 or 20 minutes, hopefully, at most. So these are the same brain, okay? This is a T1 weighted scan. This is a density weighted scan. And this is T2 star weighted scan, okay? So let's go through together. And these are the sort of the proton densities, the T1s and the T2s. And let's say the maximum TR we can do is 10,000 milliseconds, okay? And the minimum TE we can do is 2 milliseconds. Okay, so that's the system is telling you what the maximum you can do. So let's figure out together what sort of the TR and TE should be. So let's start off with the easiest one, density weighted. Okay, so what should the TR be here? So I've got, these are the T1 values, T2 values, proton densities. This means I just want to get rid of any T1 and T2 dependence. So what should I make my TR? As long as possible. So in this case, 10,000, right? Okay. And what should I make my TE? 2. Yep, good. Okay. How about the T1 weighted? What should I make my, let's say, TE? That's the easiest one. What should I make my TE? So this T1 weighted image should have no dependence on T2. Right. So what do I want to make my TE? 2. Yep, good. And what should I make my TR? So here are the T1 values, right? So the tricky thing is there's 3 of them, right? So here's the hint. Which of those 2 are the closest together? Gray and white, right? So I would want to try to maximize the contrast between these two, because this one is so far off that no matter if I pick a number that's sort of in the middle of these two, this is still going to be very dark, right? Because it's so much longer. Okay. So typically, if you have three tissues, you just worry about the contrast between the ones that have the closest values, and the other one is going to be very different from those two anyways, right? Because it takes so long to recover. So then you would just take the average of these two, and who's good at math? I'm not. Let's see, 150. So what does it turn out to be? 1100 maybe? Yeah, okay, 1100. Okay. And then let's, how about T2 weighted image? So here, TR should be what? So I want to make the T2 weighted image independent of T1. So what should I make TR? Yeah, 10,000, good. And what should the TE be? Once again, I have two that are close and one that's far away. So no matter what I do, this one sort of will always be bright, typically if I make the average of these two. So the average of those two, those are what, 40 apart, right? Or 30 apart. So it'd be 95, is that right? Okay. Okay, so these are applying the rules of thumb, right? So basically, if you are on a desert island and have no calculator and, can't do, don't want to do arithmetic and don't want to take account. So notice we haven't taken into account those proton density weighted, okay? So in your homework, you can just apply these rules of thumb and see what you get, okay? And getting to the question that Omar asked, that basically what you're going to see in your homework is the MATLAB will generate, this is what's called a tissue segmentation map. So the blue is CSF, the green is white matter, and the yellow is gray matter. Okay. And then if I pick like the rule of thumb for proton density weighted, it's going to give me this. And so this makes sense. The gray matter has the most protons, followed by the white matter. Oh, no, the CSF has the most protons, right? Because it's mostly water, followed by gray matter, followed by white matter. If I do T2 weighted, the brightest stuff I'm going to see is the CSF, because that lasts the longest amount. And if I do T1 weighted, the darkest is the CSF. And I see some contrast between gray and white, but not as much as if I do the optimal TR, okay, which is shown here. So in the homework, you're going to be given a one-line routine that actually calculates this for you, so you don't have to calculate it yourself. You're just asked to comment on why this looks better. And then for extra credit, if you want to derive that equation, which is just one line equation, but may take a few lines to derive it, then that's available for extra credit. Okay. But the idea is that as rule of thumb, this gets you pretty close, but if you can do slightly better by taking into account the proton density weighted values. Okay. And so typically in practice, obviously all our computations will take into account all the information to optimize it. Okay. All right, any questions before we move on? Okay, so I'm going to talk about a few things, not go into too much depth, but talk about things that are used in practice, just so if you hear about them, you know what they are. One of them is called the flash sequence. And the main defining feature of the flash sequence is it is a gradient echo sequence. And now you notice that 90-degree pulse has become a theta pulse. Okay, and typically that theta is going to be fairly small, 5, 10, 15, 30 degrees, much less than 90 degrees. Okay, so what's the intuition behind flash? So the main thing I want to get across is why you would do this. And so this was the, I think Axel Haas is the guy who patented flash, and I don't know how much money he made because of this, but it's used everywhere, so he probably made quite a bit of money. And this was his insight. If I apply 90-degree pulse, I have to wait a long time for this to recover. It's starting at m sub z equals 0, right? Whereas if I apply, let's say, a 30-degree pulse, right, then let's see, the sine of 30 degrees is a half, so I get half the magnetization. The cosine is 0.707, right? Square root of 3 over 2, right? Or wait, is that right? What's square root of 3 over 2? 0.85, 0.86, right? Something like that. Anyways, I'm still left with a lot of magnetization here. So it turns out that if you really want to go fast, you're better off just doing like a 30-degree flip angle, because then you're still left with a lot of m sub z, which you can use on the next repetition. So then you don't have to wait so long. Okay. And it turns out there's actually something that given a TR and T1, it can be shown that there's an Ernst angle that actually maximizes the signal you get for any TR and T1 combination. Okay. The equation is given here. You're not asked to derive it, but it is a gradient echo sequence. So there's this T2 star. But the idea is for flash sequences, we keep this echo time quite short. Okay, on the order of maybe like 5 milliseconds. So for most tissues, there's no dephasing that we have to worry about. Okay. So this is what it looks like for different flip angles and TRs. And so, for example, at a T1 of 1,000, right? Previously, we might say if it takes if my time constant is 1,000, for it to get back to equilibrium, typically it takes about 3 to 5 time constants, right? So you have to wait like 3 seconds on average, right? But 3 seconds is quite a long time to wait. Let's say you decide I only want to wait 500 milliseconds, okay? And then if you go this equation, if I pick this flip angle of 55 degrees or about 50 degrees, I get half my signal intensity. So I still get half my signal intensity, which is probably enough for most imaging. And the advantage is I can go 6 times as fast. Okay, so that turns out to be a pretty good trade-off. Okay. If I can get away with even less intensity, like 0.2, then I can go at TR of 1,000 or even 30 milliseconds. So I could go, in this case, 100 times as fast. Okay. Or in this case, what is that? 30 times as fast. So anytime where you want to do really fast imaging and you still have enough signal to be okay with this drop in signal intensity, then you'll tend to go to a flash sequence. Okay. The idea is that the sort of the intuition is similar to what you have with does everyone know what like a flush toilet is, right? Like if you have a full flush and you flush all the water from the tank, then you have to wait for the water to get back before you can do another full flush, right? But if you only flush it halfway, right, you might still have enough of a flush to do what you need to do, but you don't have to wait as long to flush again. Okay, so that's a way to think about it. Okay, so that's one thing that you'll see a lot in practice, and it's used everywhere. But the other thing you'll see a lot in practice is what's called inversion recovery. We've hinted at this before, but let me just talk about it now. So here's what we've talked about before. We have a 90-degree excitation pulse, 180-degree preparation pulse, and then we acquire our data. And we have this TR from shot to shot. Now what I do is before I even apply my excitation pulse, I apply what's called an inversion recovery pulse, which is this 180-degree pulse. Okay, so that actually, before I do this 90-degree pulse, I actually take this signal and I invert it. Okay, and then I let it recover. Okay. And it turns out that this time, Ti, is the inversion time. If this time is set according to this equation, then at this point in time, M sub z will equal 0. Okay, so that means if I have some magnetization, some tissue, I invert it and it recovers, and I apply my 90-degree pulse at this point in time, that tissue is erased. Okay, I basically erase the contribution of that tissue. Okay. So that's shown here, where basically, so for example, here, if I want to get rid of fat, so here I've inverted fat, water, and CSF. And if I wait different amounts of time, if I acquire here, I have 0 fat. If I acquire here, I have 0'd out white matter. And if I acquire here, I've 0'd out CSF. Okay. So here, you're seeing different inversion times where I've nulled out fat here. Here I've nulled out white matter, okay? And here I've nulled out the cerebral spinal fluid. So here you see I've gone from this being very white to now very black. Okay, and here I've nulled out the gray matter, which is all this tissue. So sort of see here, you're really not seeing the gray matter, you're just sort of seeing the white matter tracks and the CSF. Okay, so this is a very useful sequence. For example, let's say you had someone, for whatever reason, like a lot of edema, they had a lot of fluid, right? And it was sort of obscuring your ability to see what the underlying tumor looked like, right? So in this case, you could apply what's called a T2 flare or a flare sequence, which would null out the fluid, okay? So you get something like this. So if there was a lot of fluid, you would actually not get rid of that contribution. Okay, so this is what radiologists and radiological technicians used, depending on the case they see. If the radiologist has some prior indication of what they're looking for and then what they're looking for, then they say, well, make sure you get this sequence or that sequence. Okay. Typically at UCSD, there'll be a standard sort of protocol, for like tumor, for MS. So there's going to be set protocols that the radiologist can say, just do that set protocol. And then depending on if there's added information, they said, well, do that set protocol plus add these things. Okay, so that's what the radiologist, that's their job. And then when they get the images back, then their job is to interpret the images and make recommendations to the referring physician. Okay. Okay, so this is what inversion recovery looks like. So basically, it's just a 180-degree pulse that you apply, and then after that, you acquire image. You can even null out black blood. So this is what's called a black blood preparation. And so there's different ways you can null out tissue. You can apply, so for example, here I've nulled out CSF. Here I've nulled out all the blood around the heart, in the heart, so that you can see the vessel walls better. Okay. And then you can even do things like if you apply a lot of these pulses, you can actually null out tissue from a lot of different T1s. And so in this example here, this was a PhD thesis from Stanford where he showed that you could null out all the tissue except for blood. And so there you're actually seeing just blood. Okay, so he's nulled out all the background tissue by doing this. All right. So there's a lot of flexibility in MR, as you can see, just by understanding that, for example, different tissues have different T1s. Okay. Okay, so before we start our fMRI discussion, are there any questions? Okay, so now we're going to sort of, for the remaining lectures, it's sort of going to be more like applications, sort of trying to take the knowledge we've gained and show you sort of how you can use it to understand sort of fairly widely used methods. And so one of them that's definitely widely used in research, much less clinically, is fMRI. Okay, and so far we've really talked about, how do you get a good image of anatomy? How do you make sure you don't get aliasing? And how do you make sure you get good resolution? fMRI is really sort of saying, well, let's assume I can measure the anatomy well, but I also want to know what different parts of the brain are doing. Okay, and how are they doing it? And so that's where fMRI comes into play. fMRI is essentially like MRI, except that in a lot of fMRI experiments, the subject is actually doing something or having something done to them. Okay, so they might be playing a video game. They might be having pain applied to them. So, for example, there's some things where they have heat applied to them, like really intense heat applied to them, and we see what the reaction to that is. We might investigate them with like caffeine. We'll see what the effects of caffeine are on them. So there's lots of different experiments. Essentially, as that thing from Homer Simpson showed, essentially anything you can think of has probably been done or someone is thinking of the experiment. Okay. Functional MRI is relatively new. The first paper really showing it, there was a set of 3 papers in the early 1990s showing it. And the basic experiment is as follows. Essentially, you're taking images of the brain, and let's say you look at 3 different parts of the brain here, okay? Now, here they're focusing on this part of the brain back here. So this is your visual cortex. This is what's basically responsible for creating the image that you see in your brain, that you're in a classroom and you see light and everything. So that's your visual cortex doing all that, okay? And so in this case, they were just shining light and turning it off and on. And what they noticed is if they looked at areas in the visual cortex, whenever there was light, the signal would go up. And then when they turn off the light, it would go down and up and down. Okay, so simple experiment, but actually the first time they did it in humans. Okay. The other thing they noticed is if they changed the echo time, they could make that signal change, right? So if I picked an echo time of 40 milliseconds, they got a strong signal. And if they picked an echo time of 8 milliseconds, the signal almost went away. So this implies there's a T2 star dependence because they're using a gradient echo sequence here. Okay. This is only up to 2016, but as you can sort of see, the number of publications has sort of you know, I'm not sure if that's exponential, but it's gone a lot, okay, in terms of publications per year. So it's a very, very active field of research. So what's the fundamental trade-off that we make in fMRI? So typically with anatomical imaging, we might want to have 1 millimeter isotopic resolution. And so we might spend 6 minutes to do this, okay? But if we want to, in 6 minutes, your brain goes through lots of different states, right? So for example, 6 minutes ago at 12:04, I don't even know what we were doing, but we were doing something different than what we're doing now, okay? So 6 minutes is a long time, right? And you've probably had 100 thoughts or more in those last 6 minutes, right? So this is too long of a time scale for most studies of cognition, right? So we want to be able to go faster. So this was showing that this image here, which is just a single slice, was acquired in 60 milliseconds with a volume of 45 millimeters cubed. So that's about what, 3.5 by 3.5 by 3.5. Okay. It turns out that since this was from 2002, right now the state of the art is we can do about 8 millimeters cube, so like 2 by 2 by 2, pretty reliably. We can do the whole brain in about 800 milliseconds. Okay, so it's increased quite a lot, and a lot of this has been a lot of technologies we've talked about, parallel imaging, lots of the stuff that we've talked about how to go faster. That's come into play over the last 20 years to go from fairly slow to and fairly low resolution to 2 millimeters isotropic is not bad. Okay, and if you really want to push it, you can go even less. So there's been really increases in how fMRI works. The basic idea behind fMRI, the bread and butter sequence for most fMRI is echoplanar imaging, which is also called EPI. Okay, so when you hear the term EPI, that's echoplanar imaging, and essentially it's a zigzag trajectory that allows you to go super fast. Okay. And then as we talked about MRI, we might just we're looking just basically one image, right? In MRI. In fMRI, we acquire multiple images over time. And as we're doing those images, we might apply a stimulus, okay? And then what we're looking for is we look at a certain area of the brain and see how the MRI signal varies with that stimulus. And the simplest analysis you can do is you can just take your stimulus and correlate it with the signal in every voxel. And so you could end up with like a correlation map. Okay. And so that's the first way it's done. And most methods are still some variation of this with some more, details on how to do it. But essentially the basic idea is you're just looking for correlations between what you did and what you measured. Okay. So for example, this person was tapping obviously their right hand, okay, and getting activity in the left motor cortex, okay. So this is just typically how, we'll typically display, if you look at, if you see something like in the news, news articles love to show fMRI pictures because they look cool. It's like, you have a brain with colors on it. And so they're typically some variation of, they'll take an anatomical image and show the color map, and the color map, at least for this scan, is showing where there was the most brain activity that was related to how they were tapping their fingers. Okay. So today, let's just talk a little bit about what causes it, and then when we pick up on Monday, we'll go into more detail on the applications. But just to remind you, one of the clues is that there is this echo time dependence of what's called the bold contrast. So this stands for blood oxygenation level dependent. Okay, so that gives you a clue as to what we're measuring. Okay, so let's see why is this a blood oxygenation level dependent signal? Okay. So remember what we just talked about. R2 star has two components. There's 1/T2 plus 1/T2 prime. Okay, so R2 star is sort of got stuff due to random motion and due to static homogeneities. And to large part, this is what most of fMRI is based on. Okay. So this is the picture we just looked at. So the more inhomogeneity there is, the less signal there is. Okay. So what we saw in the fMRI is that we went from a smaller signal to a bigger signal, right? When they shine the light. So that must mean that when we shine light into someone's eyes and it goes and the visual cortex is active, we're going from a state with more inhomogeneity to a state with less inhomogeneity. Okay, so that's the first thing we can conclude, right? It's not, it could have gone either way. A priori, people didn't know which way it was going to go, but it turns out it goes this way. Okay, so let's figure out, why does it go from a state of more inhomogeneity to a state of less inhomogeneity? Okay. So let's take a look at the bold signal change. We can represent it as, at baseline, we have our echo time times some R2 star, which is just 1 over T2 star at baseline. So the signal is going to decay like that. And then since we know that the activation signal, the signal typically increases, we know that the R2 star must get smaller, or T2 star is getting longer. And so the signal is going to go up with activation. Right? And so typically what people talk about is the bold signal change, which is this activation signal minus the baseline signal over the baseline signal. And if you do a first order Taylor series expansion, that just turns out to be the echo time minus sine times the change in the relaxation rate. Okay. And since we know that this overall thing is positive, that means delta R2 star must be negative. Okay. That means the relaxation rate decreased. Okay. So let's see why that would happen. So it turns out that R2 star depends on deoxyhemoglobin. Okay. The more, and for those, just to remind you, what happens is when you're in the, as I think all of you know, that the hemoglobin molecules carry oxygen. Okay. So in the lungs, the oxygen binds to the molecules. Okay. And so every hemoglobin molecule has 4 of these oxygens that binds, right, to the iron atoms. And then when they're in the tissue, the oxygen is delivered, so it decouples from the hemoglobin, and you're left with these blue things, which are the iron atoms. Okay, so the more oxygen that's delivered, the more of these iron atoms is exposed, and the more inhomogeneity you're going to have, right? The more iron you have, the more it's going to perturb the field around it. Okay, so the basic idea is we go from a state where there's maybe some iron atoms exposed, so some inhomogeneity, and there's a state where there's a lot of oxygen atoms or iron atoms exposed, so there's more homogeneity. Okay, so what we must be seeing is we're going from a state where there's a lot of deoxyhemoglobin to less deoxyhemoglobin. Okay, so deoxyhemoglobin is the concentration of hemoglobin that's got the oxygen removed from it. All right, so this has more iron, this has less iron. Okay, so we're going to go from a state where there's a lot of iron to a state where there's less iron. All right. So what determines how much deoxyhemoglobin is in the tissue? It turns out it's a trade-off between delivery and use. Okay. CBF stands for cerebral blood flow. Okay. That's delivering the oxygen. Okay. So the more I deliver, the more oxyhemoglobin there is, right? And that's going to dilute. So that's fully oxygenated blood, and that's going to dilute how much, make it so that there's less iron. But as I use up the oxygen, that's called oxygen metabolism, that's going to tend to increase the amount of deoxyhemoglobin, right? Because I'm offloading the oxygen and exposing the iron atoms. So it's a trade-off. The more blood flow I have, this is going to go down, okay? But the more metabolism I have, this is going to go up, okay? We found out overall, because the MR signal is going up, we know that the net must be going up. Okay, that must mean that flow is sort of outstripping metabolism. Okay, and if you think about it, that actually makes sense, right? Because if you are nature and you're designing something that's going to survive, you want to make sure that there's enough delivery, right? You don't want to run out of oxygen. Okay, so it turns out that ratio, it's essentially, it's either a 2-to-1 ratio up to like almost a 4-to-1 ratio. So nature is quite conservative, It's like, oh, you need this much oxygen. I'm gonna give you twice as much as you need, so you don't run out. Okay, that makes a lot of sense because if you're running away from a tiger, you don't want to like have your brain just stop, right? You need to be going, and you need to be making the right decisions, right? So basically, everyone who has survived, right, has a higher CBF to CMRO2 coupling ratio, and probably those sort of like species or ancestors who didn't had a lower ratio probably just didn't got eaten or something like that, or they fought against another tribe that had a better ratio, and evolution has sort of dictated what that ratio is. Okay, so I think we'll end there because we're at the end of time. So any questions about what we've talked about so far? Okay, so we'll pick up again on fMRI on Monday, and then I will send out an announcement about the project twos. So thank you for most of you have submitted your proposals. So that's good. So I think those of you have submitted it. In some cases, I've asked for revised proposals, right? Because we would like you to do well on the project. So the more sort of feedback we give you early on, then hopefully that saves you time, or minimizes your surprise at the end. So feel free to ask questions if you need more clarification. Actually, it's much more enjoyable for Professor McVeigh and I if the projects are really good, right? Because we sit there and we're like, oh my God, this is great. So we want your projects to be good, okay? So take our feedback. And so if you've been asked to submit a revised proposal, your group will appear yellow in the Google Sheet, indicating that we're still waiting for the revised proposal. Once I get it, it will turn green. So please submit those by 5 p.m. tomorrow if the revision is required. Try to make your revision as good as possible. If I require more feedback, I will ask for additional revisions, but I'd rather not prolong the process too much. So those are due at 5 p.m. Tomorrow if you have to submit a revision. And so that will be considered on time because you've already submitted your first one before the deadline. So a revision by 5 p.m. can be considered on time submission. So that's fine. If you have issues, just send me an email. I mean, that's not a big issue. We can sort of be flexible. And then the other thing is, as I will also send an announcement, there will be one last homework, but it's going to have one fairly short problem on it, covering what we talked about today. So hopefully that will allow you to spend most of your time on the projects. I will also send out some additional feedback or sort of suggestions on the project on how to sort of, what to look for as you're doing the project. But in general, it's essentially what is said in the project 2 assignment. We're looking for evidence that you've sort of dug into a topic at not a superficial level, but just sort of slightly deeper than superficial level. You've tried to do something that's not just a literature review, and you've really sort of thought about your results. And so you've sort of tried to understand what do they mean, and you're not just describing what you saw, you're sort of trying to understand what you saw, okay? I think there's a question online. Will homework 6 be long? No, homework 6 will be quite short, okay? It's meant to be doable. If you really had to, you could probably do it in 15 minutes, okay? But if it takes an hour, then that's fine too, okay? But no more than an hour, hopefully, okay? So any questions before we end for today? Okay, if not, I will end the recording and we'll stick around to answer questions about either projects or the homework.